Okay, let's move on to chapter 2, which is about determinants. And first thing is determinants only apply to square matrices. That means matrices that are 2 by 2, 3 by 3, 4 by 4, or n by n. 1 by 1 is also allowed, but that's kind of simple. So we've seen them in the 2 by 2 case. So here's a matrix that has 2 rows, 2 columns, and the inverse is 1 over the determinant. And also, this determinant is denoted by delta. And what is the determinant? It's this product here, AD minus BC. So where you multiply the diagonal elements, A times D, and subtract off the off-diagonal elements. That's what this magenta arrows tried to indicate. Okay, and then to find the actual inverse, then you flip the numbers in the main diagonal and negate the numbers in the off-diagonal. So what we have here is a scalar, 1 over the determinant, or delta, multiplying this matrix. And the way scalar multiplication works, a scalar multiplying a matrix, is you take that scalar and multiply every single element of the matrix. So here our scalar is 1 over delta, so we multiply d by 1 over delta, which corresponds to taking d and dividing it by delta. And similarly, in the other spots, we also divide by delta. That corresponds to multiplying by 1 over delta. Okay, and one thing to notice is because we're dividing by delta, we can only do that if delta, the determinant, is non-zero. And so that's an important property we'll see, is that if the determinant of a matrix is 0, then the matrix does not have an inverse. And then if the determinant is not equal to 0, then the matrix does have an inverse. This holds for 2 by 2 matrices, 3 by 3, any n by n matrices. Although we've only seen it for 2 by 2 matrices, where I've given you the specific formula for the inverse. And you can see then that if the determinant is not 0, we can divide by it and find the actual inverse. Now, the formula for the determinant in the n by n case is somewhat complicated. So we have to define some terms to help us explain that formula. So the first term is what's called the minor. So suppose we have a n by n, again, a square matrix, and then this minor, m sub ij, is the determinant of the n minus 1 by n minus 1 submatrix formed by deleting row I and column j of our initial matrix A. And I'll do an example on the next slide. And then finally, an additional term is cofactor. That's where you just take this minor that we found or described in the previous line and multiply it by some power of -1. Okay, let's do an example of finding a minor and finding a cofactor. So here's a 3 by 3 matrix, and let's find the M11 minor. Well, it says we delete row 1 and column 1, and so then we're left with this matrix. So this is a 2 by 2 matrix, and we take its determinant. That we know how to take the determinant of a 2 by 2 matrix. That's the only determinant we know so far. So that's multiply the diagonal elements of 5 times 8 and subtract off the off diagonal elements, 4 times 6. And okay, then we do the arithmetic and get 16. So M11, this minor associated to the 1, 1 position, is 16. And again, we'll see why we're computing this, so how we're going to use it shortly. Let's just do another example, the M23 minor. So the 2 refers to the row, so we're in row 2, the 3 refers to the column, so we delete row 2, column 3. And so what's left over is the matrix 3, 1, 1, 4. So here I've written it here. And then we want to find its determinant. So we take the product of the diagonal elements, subtract off the product of the off-diagonal elements, and we get 11. Just as a notational remark, sometimes these absolute value signs refer to determinant of a matrix. Okay, so we found 2 of the minors. There's actually 9 different minors. For every single position, there's a minor. We won't need to find all. We'll typically just need to find 3 in order to find the determinant of a 3 by 3 matrix. Okay, and so then a slight modification of the minor is the cofactor. There you just take your minor and raise -1 to the sum. In this case, the sum or addition of 2 and 3. This becomes -1 to the 5. That's -1 to an odd power, so it's just -1, and so it's -11. Meanwhile, the cofactor associated to the 1, 1 position is -1 to an even power, 1, and so the cofactor is going to be the same as the minor. Now finally, with all those definitions a little bit strange out of the way, we can finally define what the determinant of a matrix is, of a square matrix, an n by n matrix. So here's the process. You take any row or any column, and for each entry in that selected row or column, multiply it by its cofactor, and then add up these products. There's going to be n of them, and the number you get is called the determinant. Let's do an example. That sounds a bit complicated. And we need to find the... Okay, so here's an example of a matrix, a 3 by 3 matrix, and we want to find its determinant. So the process is to pick any row or any column. And, well, okay, let's just choose something simple, the first row here, so 3, 1, 4. And so then the determinant of this matrix A is formed by going along each of these entries, so 3, 1, and -4. So I've written them down, 3, 1, and -4, and multiplying each of those entries by the associated cofactor. So 3 is in the 1, 1 position, so we need to find the cofactor associated to the 1, 1 position. The 1 is in the row 1, column 2 position, so we need to find the cofactor associated to that. And the -4 is in the row 1, column 3 position, so I need to find the cofactor associated to that. Okay, so hopefully you're with me up to here. And then the next step is to find all these cofactors. Okay, so the cofactor in the 1, 1 position, we basically focus on this matrix here, and that determinant, and take its determinant, this 2 by 2 matrix of 5, 6, 4, and 8. We multiply the diagonal entries, subtract off the off-diagonal entries. So here's the matrix associated to the 1, 1 position, and the vertical lines mean take its determinant, and that turns out to be 40 minus 24, which is 16, which, as we saw on the last slide. Okay. Then, so we found out what the, and the cofactor is -1 raised to the second power, which is just +1. Okay. Then, well, what you'll see is that the signs will alternate positive, negative, positive when you're talking about the signs that are involved in the cofactor. But okay. Then we need to find this cofactor 1, 2, and that is, let's see, here's the 1, 2 position. So we mentally at least delete row 1, column 2, and what's left over is 2, 6, 1, and 8. So we form that matrix, take its determinant, that's again what the vertical lines mean. 2 times 8 is 16, 1 times 6 is 6, subtract the 2, and we get 10, and then the associated sign is -1 to the 1 plus 2, which is 3, so it's going to be a negative. All right, and then finally, the cofactor associated to the 1, 3 position, this associated with this -4 here, we delete row 1, column 3, so we're left with this 2 by 2 matrix, 2, 5, 1, 4, and take its determinant. 2 times 4 is 8, subtracting off 1 times 5, you get 3. And again, the sign is -1 to the 4th power, so again, notice that the signs were plus, minus, plus. That will always alternate. Now there's a minus from that -4, but that's not what I'm referring to. I'm referring to the signs coming from what you need to multiply the minor by to get the cofactor. Okay, so we've got -4 times +3, and then doing the arithmetic, we get 26. Okay, and so that's our answer. That's the determinant. So we did a whole lot of work to find the single number. And you might ask, well, what's the point of that? Well, because this number is non-zero, not zero, this matrix has an inverse. Now, the formula is, we'll learn later how to find the inverse, but right now, at least we know a quick way. It's a single number tells us that this matrix has an inverse. Now, what's surprising is that if you picked a different row or a different column, so again, we've picked row 1 and we expanded along minors, that's what, or expand by cofactors is also what it's called. If we had picked column 2, we would get the same number 26 at the end of the day. The intermediate numbers might be different, but we'll get the same numbers even at the end of the day if we did the arithmetic correctly. Okay, and let me show you how to use Sage to calculate this and check our answer 26. So I went to cocalc.com and opened Sage Math Worksheets. That's what's crucial here. For other languages, there's going to be like Python or Julia. The syntax is going to be a little different, but we're working with Sage. Okay, and then here's the notation for entering this matrix. So this part here, QQ, stands for the rational numbers. That part is a little bit optional, but it's a good practice to put that field, is what it's called, the field you're working over. Now we have a 3 by 3 matrix, and the matrix in question was 3, 1, negative 4 in the top row, followed by 2, 5, 6 in the second row, followed by 1, 4, 8. Okay, so then I hit Shift Enter. Oops. Shift Enter, or hit Run. And the first time you do this, it's going to take a little bit of time as you see this blinking thing, because it's apparently connecting to the server or what have you. But after the first time, things will speed up quite a bit. Okay, so now it's stopped blinking, and well, nothing appears to have been done, but that's just because all we've done is assigned A, and then we can ask what is A. So A is this matrix here, and that's the matrix we had. Okay, and then to find the determinant, we just type in A dot determinant and empty parentheses, and then hit Run or Shift Enter, and then we do indeed get 26. While I'm at it, let's just try to figure out or ask how to find its inverse. And to do that, we just type in A dot. First of all, if you don't remember any of the commands, which is certainly fine, if you type A dot and hit Tab, you can get all the methods associated to this object. And then let's just type in, click on inverse, and close the parentheses, hit Shift Enter, and then here we find what the inverse is. So then let's make B to be the 3 by 3 identity matrix. Identity matrix 3. So this is the command for the 3 by 3 identity matrix. Let's see what B is. That's this. Okay, great. And then, so I want to introduce the augment command. A dot augment B. And so all that does is takes our original matrix A and augments or adds the matrix B, which in this case is the 3 by 3 identity matrix, right over to the right of it, to the right of the matrix A. Now sometimes it's nice to have a vertical bar separating the two, and so if you want to do that, you can type in an extra command called subdivide. So A dot augment B subdivide equals true, and okay, so there we've got this line that separates the two matrices that we started with. Okay, and then finally, again, I'm trying to find the inverse of A, and in chapter 1 we found that if we row reduce this augmented matrix, we'll end up with the inverse. So let's do, you can either give this matrix a name, like C is equal to whatever I've typed up here, but I'm going to just be a bit lazy and do A dot augment B subdivide equals true, And then to that matrix, I'm going to add in the method reduced row echelon form. Hope it works, and it indeed does. What we get is the matrix over here, and let's again, for comparison, see what A inverse was, and that's indeed the exact same thing. Okay, so finding determinants is, by hand anyway, is a very tedious process, no question about it. For 3x3 matrices, there's a little bit of a trick called the arrow technique. But again, it's only for 3x3, not for 4x4 or higher. And so here's what it is. Okay, we have this matrix, the same matrix we had on the previous slide, and you just copy the first two columns over. So here's the first two columns, and then you copy them over. And then the formula is you take these three diagonals here and multiply those. So 3, 5, 8, multiply the numbers in those. 3 times 5 times 8 is 120. 1 times 6 times 1, that's 6. Negative 4 times 2 times 4 is negative 32. Okay, so once you have all that, basically then you do the other three diagonals out here and subtract that. So 1, 5, negative 4 is here. That's multiplies to negative 20. Then 4, 6, 3, that's here. That multiplies to 72, and then 16. And then you add up all those, that's 68. And then you subtract from the first number that you found that was formed by adding up these three diagonals, the products of the entries there. And okay, we happen to get 70 as 26 as before. So again, this is this is just another technique. It only works with 3x3 matrices. Not the most crucial thing to know.